Alright everyone, so sorry I can't be there today. I'm taking care of some doctor's appointments and things like that today. So we're going to continue on with the notes that we didn't quite finish last time. This is the second part of it. This is where we are talking about motional EMF. Remember, the EMF just means voltage, right? It's just the electromotive force is what EMF stands for. It's not really a thing anymore, but we still call it EMF. It just means a voltage source. So Faraday's law was that the EMF is equal to the negative change in flux over the change in time. Okay, so we're going to keep that in mind. Another way that we can say this in a different context is that we could say that EMF is equal to B, the magnetic field, times L, the length of a bar that's moving, and V, the speed of that magnetic, the speed of the bar and through that magnetic field. So a bar must be what it says cutting through field lines. And you'll see what that means here in just a second. It cannot be moving parallel to the field. This formula is easily derivable from Faraday's law of induction. So if this is Faraday's law, right, epsilon, or EMF, is equal to the change in flux or the change in time, that can be rewritten as epsilon is equal to the change in, that's a delta, change in B times A over time, B times A. Now if we're thinking about like something down here where we have this rod that is moving to the right, then our area is literally changing. The area that is encompassed by our wire is literally changing. Where we have L, the bar, and then we have this length down here that we could call W. Now that W, actually I don't want to call it W, let's call it delta X, just because W means lots of things. So that delta X. So that delta X is changing in time. But that delta X is currently what the length is of the square or the rectangle or whatever is down here. So what if we did that this is change in B times A, but A is L times delta X over the T. Well, the delta X over T, that's just distance divided by time. So the equation becomes B times L times V. So really this delta over here got moved to that delta X right there. So that just means that if we have this long wire or a rod moving in a magnetic field, and we have this wire set up here, then that wire, the rod, is basically acting like a battery. And you can think about this as, okay, that rod is carrying charges. So let's say for a second that it's carrying positive charges. We have all these positive. Let me do something that's not so thick. Let me change this color. So we have positive charges, right? Positive charges. Now those positive charges are moving to the right. So we could say the right-hand rule. This is the right-hand rule number one, the flat hand, the one that has the middle finger almost flipping everyone off, where we say that we have charges that are moving to the right, so our velocity is moving to the right. We have a magnetic field that's going into the page. So if you were to use your right-hand rule, you would say that they feel a force upward. So the charges that are in that rod feel a force upward, okay? But when those charges get to this point right here, where are they going to go? Well, they feel a force upward. They can't go to the right because there's nothing there. There's an end here that they can't really go through. So that means they'll go along the wire until they get back down to the edge of the rod and then continue their journey again. So by virtue of having this rod moving in the magnetic field, we have created current. Okay, we have created an induced current. So how much current flows through this resistor? Well, we first calculate the epsilon, the voltage source. So epsilon is equal to BLV. If our B is 0.15 Tesla, our length is 50 centimeters, and our velocity is 2 meters per second, then that would be 0.15 Tesla multiplied by the length, which is 0.5 meters, multiplied by 2 meters per second. Okay, but if we want current, then we'll divide this by the resistance. So we'll divide all of this by the 3 ohms that we have. So 2 times 0.5 just gives you 1. 0.15 divided by 3 gives you 0.05. 0.05, and the unit would be amps. And which way would it be going? So we already said that the forces on the rod are going to drive charges upwards. So when they get around to the resistor, they're going to be traveling down. So it's going to feel 0.05 amps of current, and it would be going down. Or you can say in the loop itself, it's traveling in a, what is that going to be, counterclockwise direction. Now, what's really interesting is that we were talking about last time that this change in the area that we're seeing, that's a change in flux, right? So let me do this in a different color. So the fact that we have an area right here, is that area going to be going up or is it going to be going down? So in this case, we have an area that's increasing, right? Area that's increasing. So we have flux that is increasing, and it's increasing with the magnetic field that's going into the page, right? So according to what we were talking about last time, is that Lenz's law and Faraday's law says that we're going to set up a current that is going to try to stop that from happening. Okay, and by stopping that from happening, it's going to set up a current that has its own magnetic field. So if we're getting more current or more magnetic field that's going into the page, then our current is going to try to set up dots, right? It's going to try to set up a magnetic field that's going out of the page. So I want you to think about grabbing that rod with the current going up towards the top of the page. If you curl your fingers, you'll see that they'll curl around to give you a magnetic field that is going out. So that's two ways of looking at the same thing. We can use the right-hand rule on the charges that feel a force to go up the rod, or we can use the right-hand rule with Faraday's law and showing that it's going to set up a magnetic field that is opposite of that change in flux that we're seeing. Either one gives us the exact same thing. And that would be a counterclockwise current. All right, so how much current flows through the resistor? Well, we just did that, right? So this is just we've already done that, 0.05 amps. Okay, so how much power is dissipated by the resistor? So power is equal to, one thing is V times I, and we could definitely do that. Our voltage here would just be the BLV times the current, which is 0.05 amps, or we could just do it like this, I squared times R. So it would be 0.5 amps squared multiplied by the resistance of 3 ohms. And we would get 0.0075 watts. All right, which direction is the induced current through the resistor, up or down? So we've already figured that out. It's down because it's a counterclockwise current. Assume the rod is being pulled so that it's traveling at a constant 2 meters per second. How much force must be applied to keep it moving at that speed? So we have to think about this in a kind of a different way. So we have this rod, and that rod has a current that is going up, right? So there's our current. We have a magnetic field that is going into the page. So our right-hand rule in this case for ILB, so our force that it feels is going to be equal to I times L times B. And that force, according to the right-hand rule, is a force that's going to be going to the left. So the rod is going to be experiencing a force to the left. And so you can think about it again. You can try to do your right-hand rule. So the current is your thumb that is going up towards the top of the page. Your index finger or pointer finger is going to be going the magnetic field going into the page, and then your middle finger shows the direction of the force. So that would be going to the left. So that means how much force do we have to put on there? We have to put the exact same amount of force, but going in the opposite direction. So that means the force that we have to have on it. Now, why does it have to be the same? We were told that it was a constant 2 meters per second, so it's going to be the same force. So all we have to do is calculate ILB and then say it's going to the right. So the current is 0.05 amps. The length is 0.5 meters. The magnetic field is 0.15 Tesla. And when you put all that together, you would end up with 0.00375 newtons, and it would be to the right. This brings up an interesting question. So why does the rod feel a force going to the left? Just because it's going through that magnetic field. So it's very interesting. Let's think about this in terms of energy. So we by virtue of having this rod move to the right, have created a current that's going in a counterclockwise direction. That seems like we're creating energy out of nothing. Well, that energy has to be coming from someplace, and it's coming from the kinetic energy of the rod. So if we let the rod just go, then it would eventually slow down, because the kinetic energy it had would be transferring into the electrical energy of the current going around. So if we have to keep this moving at a constant 2 meters per second, then that means that we have to be doing work. We have to be pushing the rod along so that the work that we do gets transferred into the electrical energy that the circuit gets. So we're not creating energy out of nothing here. That energy is coming from someplace. How much power is needed to keep it moving at that speed? So power is equal to force multiplied by the average speed, or the average velocity. So our force would be 0.00375 newtons multiplied by 2 meters per second. So our power, lo and behold, 0.0075 watts, which is the same power that the resistor is dissipating. So we are giving that resistor the same thing. Alright, so let's keep moving on. So looking at Faraday's law a new way. So this is Faraday's law, right? The negative d flux over dt, or the derivative of flux over the derivative of time. So one of the things that we saw back when we were doing electrostatics was that negative the integral of E dot dr is equal to voltage, or we can say that the integral of E dot dr is equal to the negative voltage. So that means this equation right here is just a natural follow-through of that the integral of E dot ds, or E dot dr, is equal to negative the change in flux over the change in time. So where does that come into play? So let's take a look at the sample problem. So a circular magnetic field of radius 1 meter is decreasing at a rate of 4 milliteslas per second. What is the magnitude of the induced electric field 0.5 meters from the center of the magnetic field during this time? What about at 1 meter and at 1.2 meters? All right, so if we draw a picture here, then we basically have this area where we have a magnetic field, and that area has a radius. The radius is 1 meter. And then we have a change in the magnetic field over the change in time, which is equal to 4 millitesla per second. We want to know the electric field at certain points, and I'm going to kind of get rid of that because I didn't leave myself some room for a couple of things. So we're looking at the electric field at certain points. One of those points is within the magnetic field, so in through here. So that's almost like we are creating an Amperian loop, and that's kind of what that interval up there is showing us. Then we're going to do it along the surface of the magnetic field, not really surface, but along the edge of it, and then we're going to do it outside it. So, part A, we have the integral of E dot ds is equal to the change in flux over the change in time. Now, what's changing in our flux? Remember, our flux is BA times cosine theta. Is it cosine theta? Anyways, BA, the theta is not going to matter here. So it's the B that's changing. So what we really have is dB over dt, or delta B over delta t, multiplied by A. And that's our change in flux over a change in time. So E dot ds, that's going to be electric field multiplied by ds, ds being the little line segment that happens on our Amperian loop. So in this case would be the circumference of that circle, be 2 pi multiplied by the radius, and the first radius that we're doing is 0.5. Sorry, I have decimal place in the wrong spot, 0.5 meters. And that's going to equal our change in magnetic field of 4.0 times 10 to the negative 3 teslas per second, multiplied by the area of pi, multiplied by the radius squared. Now, the radius that's inside that has magnetic field is the same as the radius that is over here for our Amperian loop. So you can see some of these things. Pi's cancel. One of the 0.5s cancels. So our electric field would just be, well, we divide over here the 2. So 4 times 0.5 gives you 2. 2 times 2 divided by 2 is 0.001 volts per meter. So I have this change if we were in a different place. So let's do it. So our integral of E dot ds is equal to, again, our change in magnetic field over our change in time times the area. Now this is going to be where we're at, r equals 1. So this would be our electric field multiplied by 2 pi times 1 meter, which is equal to 4 times 10 to the negative third Tesla per second, multiplied by pi times 1 squared. Okay, pi r squared, right? So one of the ones goes away, and it doesn't really matter because it's 1, so pi. So our electric field is equal to 0.002 volts per meter. All right, so how does this change for the last part when we are at 1.2? So our electric field, I'm going to do this in a different color. So our electric field, E dot ds, is equal to the same change in magnetic field over change in time times the area. That's area, by the way, I just noticed. So that's E multiplied by 2 pi times 1.2 meters equals 4 times 10 to the negative third Teslas per second. Now we have something interesting happening here. So our area is pi multiplied by 1 meter squared. So why is it 1 and not 1.2? It's been the same thing on left and right up until this point. So we have to remember that if we go back here, the magnetic field is only to a radius of 1. So our Amperian loop might be all the way out to 1.2, but the magnetic field only has an area in 1 meter. So that's going to be a 1, and it's 1 squared, so it's not really like it's even there. So our electric field then would be, pi's go away like they did before. You end up getting 1.67 times 10 to the negative third volts per meter, negative third. Or that would be 0.00167. So that finishes out the notes. So there's a couple of free response questions that you should get. Either the sub's going to hand them out to you, or they might be in the tray that you picked up on the way in. But the first one looks like this. So I want you to take a crack at it. So I want to pause the video and give you about 15 minutes or so to take a crack at it, and then we will go over this one in particular. All right, so pause this video and work on this free response question for about 15 minutes. All right, welcome back. So let's take a crack at this. So we have this long, narrow, rectangular loop of wire shown above, has vertical height h, length d, resistance r. The loop is mounted on an insulated stand attached to a glider which moves on a frictionless horizontal track with an initial speed of v0 to the right. The loop and glider have a combined mass of m. The loop enters a long, narrow region of uniform magnetic field B, directed out of the page toward the reader. Express your answer to the parts below in terms of B, D, H, R, M, and V0. What is the magnitude of the initial induced EMF in the loop as the front end of the loop begins to enter the region containing the field? So by the front end, it's saying that the loop has not completely gone all the way in yet. So the only thing that's going to be causing an EMF is the front edge of the loop is going to be in there, and that has a length h. So we can actually use the second form of the Faraday's law, that epsilon is equal to BLV. But we have to put things in terms of the stuff that's been given to us. So we can use B, that's the magnetic field. But instead of L, we have to use H. And then V in this case would be V0. And so that's it. That's all you got to do for part A. It's not too terrible, right? So let's take a look at part B. What is the magnitude of the initial induced current in the loop? So we are given the fact that the whole thing has a resistance R. So if we know the induced voltage, then we know the resistance, or our current would just be voltage divided by resistance. In this case, BHV0 divided by R. And that's it, because we don't have any numbers to be able to do anything. All right, so I'm going to draw a little picture here so we can do this part for C, and it's going out of the page, so I'm going to make some dots here. So there we go. Okay, so let's ask ourselves what's going on here with our flux. So we know our flux is increasing. The magnetic field is out of the page, right? So we want to make sure that we are setting up a current that is trying to fight what's going on with this. So we want to set up a magnetic field. The new magnetic field needs to be going into the page. So if we try to grab our wire to make something go into the page, then you see that the current that happens to do that is a current that sets up like this. So that means our current is going to be a clockwise direction. So this thing is going to set up a magnetic field that's going into the page. So it's going to try to combat the change in the flux that's happening with it moving into the field. Okay. Part D, derive an expression for the velocity of the glider as a function of time for the interval after the front edge of the loop has entered the magnetic field, but before the rear edge has entered the field. All right. All right, so we got our work cut out for this one. So we're looking for a velocity function. All right, so we saw in the notes that when something like this happens, when we have a motional EMF, that energy's got to come from someplace, and that place comes from the kinetic energy. And there's a force that's trying to slow down that motional EMF. So let's try to figure out what that force is going to be here. So our magnetic force would be equal to ILB. The sine theta is not going to matter here. So that's going to give us I, which we solved for earlier. BHV0 over R multiplied by L, which is still H multiplied by B. So that means our magnetic force is going to be B squared H squared V0 over R. Now we are going to set up the fact that our force is going to be going backwards to our motion. So velocity is going forward, so the force is going backwards. So we are going to say that then our magnetic force is going to be a negative. Now if this equals mass times the acceleration, as it should, right, Newton's second law, then we can say that dv dt, right, which is acceleration, is equal to negative b squared h squared v0 over mass times the resistance. Right? So our thing about this is that we have to get our v's to one side and our t's on the other side. So see if I can do this with the amount of space that I have left. So we would have dv over v. And that would make sense. So we're going to say that this is dependent on velocity, and so we're going to get rid of this v0 and just say that the initial velocity is v0. And say that we need a function versus velocity, so we're just going to keep all of our v's as just regular v. So that, in this case, we have dv over v is equal to negative b squared h squared mass times resistance dt. We would integrate this from v0 to v, because our initial velocity is v0. We would integrate this over here from 0 to t time. So the left side would give us just a natural log of v between v0 and v. This side would give us a negative b h, and those are both squared, over m times resistance times time. Technically from 0 to t, but you know that 0 is just going to go away. So this would be the natural log of v minus v0. I guess that's actually the natural minus the natural log of v0 is equal to all that stuff. That would put us that V over V naught is equal to E to all of that stuff, negative B squared H squared T over MR, which gives us that V finally is equal to V naught times E, negative B squared H squared T over mass times resistance. And there we go. It's an exponential. This is kind of like the exponential decay that we see with charge piling onto a capacitor. So we're getting that energy from someplace, and that someplace that we're getting the energy from is decreasing, that sort of thing. So our velocity is decreasing in this case with an exponential function. All right, so in this one we're sketching a velocity versus time function, and you think it would just be the function that we just got, but here's the thing, is that we only have that function when we have the induced current, right? So we got that as from the idea that we have a change in flux, so that sets up an induced current. Then induced current has a force backward on it. So that only happens until we get to T1, and because it says T1 is when the back has entered the loop. We no longer have a change in flux, which means we no longer have an induced current, so we'll have an exponential decay until that point, but once it's inside the field, it will just stay constant because there's no energy conversion anymore. There's no electrical energy being converted. Until it gets to T2. T2 is when the front edge starts to leave the field, and then we'll set up a new current, and that new current will still be producing a retarding force on the wire, and so we'll have another exponential decay until T3 when it completely exits the field, and then we're just ending up with another flat line until T4. All right, so there's our function. These are the exponential functions that we solved for in the previous part of the problem. And then we have to realize that we have no velocity change, no acceleration, because there's no force due to the induced current during these sections. All right, so you have one other free response question, and that is this 2007 E3, and I'm going to let that one be yours to have. So I want you to figure it out, and if you have any questions on it, you can ask whenever I get back on Friday. All right, I appreciate it. Let me know if you have any questions. You have WebAssigns that are due over the motional EMF stuff and the electromagnetic induction stuff. That's due on Friday, so if you get through with this before the end of class, you can always check on the WebAssign. All right, have a good one.